Hello everyone. You know what is an integer? If an equation has integer root, then the integer root must satisfy the given equation. All those polynomial or algebraic equations might have a rational root, might have an integer root. You will say that what's the need to discuss it separately, because the root will always satisfy the equation. From there we can decide what kind of root it has. No, here in today's class we are going to learn a technique which will help us to decide the root and whether it is integer or multiple, that we'll be able to determine. Okay? Now let us start with the equation that fx equal to a0 x to the power n, a1 x to the power n minus 1, this way up to an. These are all coefficients, a0, a1, a2, n, these are all coefficients. And we are going to discuss whether it has one integer root or not. Before that, integer is a special case of this real number r equal to p by q. You know, if q is 1, then r equal to p is an integer. Initially when you are saying let r equal to p by q be a rational number, then you know q is not equal to 0 and pq are prime to each other. P and Q are prime to each other. Now let us find the condition for r equal to p by q as a root of the equation fx equal to 0. If r equal to p by q is a root, then a p by q must be 0. What does it mean? This means p by q to the power n, a1 p by q to the power n minus 1 plus an equal to 0. Now this you need to simplify, you write a0 p to the power n by a1 p to the power n minus 1 by therefore a1 q this way you can write that q square p to the power n minus 2 plus an q to the power n equal to 0. Okay. Now this last term contains q. Let me express the equation in this form, that a0 p to the power n equal to, take minus q as common, that is a1 p to the power n minus 1, a2q multiplied this plus an q to the power n minus 1. Now you assume that all those coefficients are integers. We are going to discuss about integer roots. Assume that you should make this assumption that let A0, A1, N be all integers. Okay? Then, if they are all integers, you can see that this whole thing going to be an integer because PQ are integers, they are prime to each other. And we have assumed all these A1, A2, A3, AN, they are integers. So, bracketed term will be an integer. Q is an integer. A0 integer, P to the power n or P is also integer. Okay? All these are integers. Now you observe that left hand side is A0 P to the power n and right hand side Q. And we know that P and Q will not divide each other. They don't have a common factor at all. They do not have a common factor. So, it's quite obvious that we can state as Q does not divide P. We are writing by this. Q does not divide P. So, Q must divide what? A0. Am I clear? Because left hand side product of two terms. One term repeated. Doesn't matter. This one is an integer. And Q does not divide. So for equality, I mean LHS equal to RHS, Q must divide A0. Agree with me? P by Q we have considered P by Q as rational root. Now one condition we got here that Q must divide A0. This is very important. Okay. Now let's decide about P. See, in this expression only, from this one only, rewriting the above equation, what will I get if we rewrite? Then this is going to be, keep an q to the power n one side, and let me write the term just before it. What about the term just before it? For your better understanding, it is an minus 1 q to the power n minus 1, isn't it? Now keep an q to the power n. When you are rewriting, you keep an q to the power n one side. So keeping this side, transferring all the terms on right side. So it is minus a0 p to the power n, a1 q p to the power n minus 1, a2 q square p to the power n minus 2 up to an minus 1 q to the power n minus 1. Isn't it? So this implies that n q to the power n minus, just a minute, an minus 1, when you are writing, there will be a p over there, isn't it? That p I forgot to write, you must take a p over there. That's why I took this term separately. Now on the right hand side, this p is a common factor. Just keep it outside. By keeping p outside, what you get? Keep p outside. A0 p to the power n minus 1, A1 q, A2 n minus 3 plus n minus 1 q to the power n minus 1. Again, left hand side, this whole thing integer, right hand side integer, and you know p will not divide q, will not divide q. So to keep this one in the form of equality, this will imply that p must divide an. P has to divide an. Now go for that equation. It is A0 x to the power n, A1 x to the power n minus 1 plus an equal to 0. You have taken p by q as a root. This p by q is a rational number. The condition is p must divide an and q must divide a0. Isn't it? We have just proved. Q divides A0 and P divides An. So if the equation has a rational root, this equation, this is the condition that the denominator must divide the coefficient of leading term and numerator must divide the absolute term. Now you just assume that you have expressed the equation where A0 is not there. If even initially A0 is there, you make it 1 just by dividing by A0 both sides. So I am just writing here, if A0 equal to 1, then what have you seen? That Q must divide A0. Q must divide 1. Isn't it? Q must divide 1. What does this imply? Q will be 1 only. That Q not equal to 0 and Q is a positive number if you take. Otherwise Q will be plus minus 1. Isn't it? So this time, what is your observation? Q will be plus minus 1. That rational number changed to this form. That is plus minus p. P is an integer. It is an integer. So let me explain this part. If you find that A0 is 1, then R equal to P by Q is P by 1 or P by plus minus 1 is going to be an integer root. So for rational root, those conditions that Q divides A0, P divides A1 to be maintained. And for integer root, we will just say that, what about this P? P divides An. So this you know, this is just established. This implies that the integer root, it may be an integer, the integer root P must divide An. This is really very helpful to find the integer roots of an algebraic equation. Now this concept that integer root must divide the absolute term, we need one application. Let us take this direct application that find all the integer roots of this equation. What is that? x4 minus 2x cube minus 2x square plus 3x minus 18. So we start this manner. Let p be the integer root. It may be an integer. For that integer p by q, whatever you take q, that must be co-prime and q must not be equal to 0. So p can be any integer when you are writing r equal to p by q. So just by the above theorem, what is a0 here? 1. That's why you dare to assume that p be the integer root. So a0 is 1 and a1, a2, a3, a4. a4 is minus 18. What have we proved? P must divide minus 18. So this implies P may be plus minus 1, plus minus 2, 3, plus minus 6, plus minus 9. Hope that we don't have to wait up to this thing. We get all the integers before it. If not, that also will be able to decide. Now let us start with this solution. That equation has integer roots of this form. So we go on putting, just put one or two values over there. For p equal to x equal to plus minus 1. This is our common sense. It can never be 0 because minus 18 is there. That x4 minus 2x cube not equal to 0. Therefore, x equal to plus minus 1 are not the roots. This is not good approach. You should start with separately. For p or x equal to 2, we observe it is 16 minus 16 minus 2x square, that is 8 plus 6 minus 18. This is not equal to 0. Can't be root. Now let us check with p equal to minus 2. This is 16 and this one plus 16 minus 8 minus 6 minus 18. This is going to be, therefore, x equal to minus 2 is an integer root. You can go for direct factorization now, but fourth degree, let us try to find another one. Let me check with x equal to 3. Then it is 81, 2 into 27, 2 into 9, plus 9, minus 18. So 18, 18, 36, 36 and 90, and here this one added 90. So therefore x equal to 3 is an integer root. Will you continue this way? Putting minus 3, 6, 9? No, you wait. You got two integer roots here, that is minus 2 and 3. The concept so far developed as their roots. So their product as their root. This implies that their product. What are the product? That is, what is the product? X plus 2, x minus 3. this is going to be x square minus x minus 6. Just check. Now x plus 2x minus 3, they both divide this one. So their product also must divide. So here it got a factor over there, that is a quadratic factor. We can rewrite the equation now, that is x4 2x cube 2x square 3x minus 18. We are going to factorize it, better to say. How many times can you divide with this term? Thrice maximum. So let me follow the protocol. Maybe it will be completed here. So x4 minus x cube minus 2x cube done, minus 6x square plus x square. So minus 5x square. We write plus 3. Check. X square adjusted. Minus 3x plus 6x. 3x adjusted and 18 also. Done. So x square minus x minus 6. This one when you factorize you will get minus 2 and 3. This one, if you make this thing 0, this implies that x equal to 1 plus minus b square minus 4ac by 2. This does not belong to set of integer. This is not in I. Complex numbers are not ordered. You can never refer them integers. So only integer roots are minus 2 and 3 over there. Hope you have understood. Okay. Now let us start with the concept of multiple root. The algebraic equation be fx equal to 0. Let alpha be a multiple root of fx equal to 0 and alpha is of order r. Then how can we express fx? Maybe other roots are there. So we can write, fx equal to x minus alpha to the power r multiplied by phi x. Phi x is the quotient when fx divided by x minus alpha to the power r. Okay. So otherwise that phi x may be 1, only roots are alpha only. Maybe, but may not be. That's why we like this final. So alpha is occurring r times. What about f dash x? Differentiate. This is going to be r x minus alpha to the power r minus 1 into phi x. This plus x minus alpha to the power r multiplied by phi dash x. So take x minus alpha to the power r minus 1 common. This will be r into phi x plus clear? So you got if dash x equal to this thing. X minus alpha to the power r minus 1, r into phi x, x minus alpha multiplied by phi dash x. So what do you observe between this and this 1 and 2? Alpha is a multiple root of order r here. Can't I see that this equation has alpha is a multiple root of order r minus 1, that we can say. If we continue this one, this is not the class of differentiation, if double dash x, similarly, if double dash x has alpha as a multiple root of order r minus 2. If double dash x has alpha as a multiple root of order r minus 2. And if you differentiate again, this way if you continue, f triple dash x, this has alpha as a multiple root of order r minus 3. Agree or not? You should. Now, one thing is very obvious, that in 1 and 2, we can draw a conclusion from there, that if you observe here, then x minus alpha to the power r minus 1 going to be the HCF between 1 and 2. Am I clear? So this implies that x minus alpha to the power r minus 1 is the HCF between fx and f dash x, and this is going to help you to find the multiple root of an equation. If by differentiation you get, it's fine to find the HCF. If you don't get, then you have to find the HCF by using synthetic division or by normal division method. Okay, so let us take one example where we are going to find the multiple root of an equation by using this concept. Hope you have understood. This way, if I continue that f in x in times, if it occurs, has a multiple root, does it have multiple root of, no, order r minus n, that is not possible. If in x, you will get a constant over there. You can reach up to n minus 1. Okay? If you go by n minus 1, then it has multiple root of order what? r minus 1, that is 1. So in fn minus 1x, it will be occurring once. If the multiple root is of order r of the given equation. Okay, let us solve one example where we can find its application. Take this equation. 1 is a multiple root of this equation of multiplicity 3. The equation is what? That is x to the power 5 minus 5x cube 5x square minus 1. So we go by that method. Find the HCF of fx and f dash x. 5x 4, 15x square plus 10x. F double dash x, this is what? 20x cube, 30x. If you take 10 as common, then this is going to be what? I wanted to make some observation here that for x equal to 1 this is vanishing. So let us take some step to find the HCF between f dash x and f double dash x. Why? If I get say x minus 1 as HCF, then x minus 1 going to be multiple root of order 2. Okay, let us go for another one. F triple dash x. 60x square minus 30. 30 LCM. 2x square minus 1. Will there be HCF? Let us find. This one quite obvious, x equal to 1 is not a factor of it. So let us find the HCF between that f dash x and f double dash x. Okay, between these two. You just write it in this manner, because here there is 20, I need a 20 over there. So just multiply 4 with f dash x. It is 20x4. What do you do by your method? We divide this by this. Synthetic division or long division, whatever, same thing. 20x4 plus 40x. So now you take x over there. 20x4, 30x square, 10x. $30x minus 30 x square minus x. Okay, HCF not completed. Let me write 10 into 2x cube. So we'll just check with this and this. You know how to find HCF. It will be 2x cube. You take 2x over there, 2x cube minus 2x square. Take plus 2 over there. So minus x plus 1. That minus x plus 1 can divide x square minus x. If you take minus x over there. So done. So you got HCF minus x plus 1. That is HCF between which two? Minus of x plus 1 means x minus 1. Okay, x minus 1 minus x plus 1, whatever you say. Whatever. That this one, these two has a multiple root. Okay. X minus 1 is a factor of this. So x minus 1 occurs how many times? Occurs once. Here x minus 1 occurs twice. And here x minus 1 occurs thrice. Isn't it? So x minus 1 will be occurring 3 times over there. This only you are supposed to prove. Prove that this equation has 1 as a multiple root of multiplicity 3. I hope you have understood the concept. Now this is the time to practice. I hope I'll be able to share the link of worksheets which you need to practice always. Okay?